Okay, so and the aim is to complete first 5 chapters of this book, An Introduction to Q Analysis by Warren P. Johnson. Today we are going to discuss sort of the first 2 chapters, like a basic introduction of the topic, but I mean, in the next session, we'll elaborate more on some of the topics. So the first thing that we need to know are inversions of a permutation. So, I mean, for us, permutations will not appear so much, but for us, permutations are bijections from the set of natural number to the set of natural number. Okay, and we'll denote it by this sigma will be something like this. So 1, 2, 3 up to n, and then sigma 1, sigma 2, sigma 3 up to sigma n. So this is the notation that we are going to use if we are going to use it. But I mean, or this is so another notation that is much easier is this. So we'll just write the sigma i's. Anyway, so let's look at it. So what is an inversion? An inversion is a pair. So I mean, an inversion will be something like ij. Okay, is an inversion if I is less than j, but sigma I is greater than sigma j. So this is what we mean by an inversion. Let's look at an example. So 1, 5, 3, 4, 2. So here there are 5 inversions. So we'll look at each pair of numbers and then we'll see which are the inversions. So for one, we don't need to do anything because so if the first number is a 1, so this is the sigma. Okay, so this is equal to sigma 1, sigma 2, sigma 3, sigma 4, and sigma 5. So basically sigma 1 is 1, sigma 2 is 5, and so on. So if the first number is a 1, then we don't really need to check because everything else will be bigger than 1. So this 1 we can forget. Let's look at the 5. So for 5, actually all the 3 pairs, 5, 3, 5, 4, 5, 2 will be inversions because this 5 is corresponding to sigma 2 and the 3, 4, 2, etc. are corresponding to 3, 4, and 5. So for each of these cases, the I is less than j is satisfied because this corresponds to 2, 3, 4, 5. So 2 is always less than 3, 4, 5. But the sigma I, which is 5, is always greater than all of these sigma j's. So 5, 3 is an inversion, 5, 4 is an inversion, and 5, 2 is an inversion. Okay? Then if we look at 3, we'll see that there is only one inversion, 3 and 2. Because 3, 4 is not an inversion because sigma I is less than sigma j in that case. Again, the last pair, 4, 2 is an inversion because 4 is bigger than 2. So in total, there are 5 inversions. And we'll write this number as, so number of inversions in sigma equal to 5. Okay. So another notation is in, which is actually the total number. So this is basically sum over all the inversions sigma, where sigma is in Sn. So basically this is the number of inversions in all permutations of Sn. So Sn is the symmetric group on n letters. Right. So this is the notation. So so we can find a recursive formula as well as a proper explicit formula for in. First, let me state the recursive formula. I'm not going to prove it. I'm just going to say, I mean, let me write down the formula first. So this is the formula for the number of inversions on n plus 1 letters. So n plus n minus 1 up to 2 plus 1 plus 0 plus n plus 1 in. So this, if I write it in a more compact manner, I'll get this as n plus 1 in plus n factorial n plus 1 choose 2. Okay, so this is the more compact notation. So there is a combinatorial way to look at this, actually, how to find this inversion and how to find this recursion. So consider you have a permutation sigma on n letters. Okay, so I have something, so like I have sigma 1, sigma 2, and so on up to sigma n. So this is my permutation on n letters. I want to insert n plus 1 now into this permutation. So I want to basically insert n plus 1 into sigma so that I get a permutation for n plus 1 letters. Now this n plus 1, I can insert here, and so on until I can insert here, or I can insert here, right? So there are n plus 1 positions for me to insert this n plus 1 into a permutation. So for example, if I look at the previous example, so 1, 5, 3, 4, 2, if I want to insert a 6, I can insert the 6 here, 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 or here. So basically there are 6 positions for me to insert the 6, right? So if I insert n plus 1 here, then everything that follows, all of the pairs of numbers, so n plus 1 sigma 1, n plus 1 sigma 2, and so on up to n plus 1 sigma n, all of these pairs of numbers will be an inversion because n plus 1 is bigger than all of these numbers, right? So there will be n inversions which will come out of inserting this n plus 1 in the first position. So this n comes from there, okay? And this n factorial comes from the total number of possible sigmas on n letters, which is n factorial. So similarly, I can insert the n plus 1 in the second position. So if I insert it in the second position, then I'll have n minus 1 inversions, which is here, and so on, okay? But we still have to count something else. So this, so these are actually the total number of inversions for, so how do I say? So we are counting a little bit less, slightly less here. So the thing that we're counting less is exactly this. So let's look at an example to figure out how to do that. Okay. So I mean, maybe this is a good example. So I will insert a 6 here. Okay. So if I insert the 6 in the first position, then all of these will be inversions. So 6 1, 6 5, 6 3, 6 4. And 6 2. This will be, all of these will be inversions. If I insert the 6 in this position, then 6 5 will be an inversion, 6 3 will be an inversion, 6 4 will be an inversion, and 6 2 will be an inversion because 6 is bigger than all of these, right? So if I insert the 6 in the third position, then 6 3, 6 4, and 6 2, correct? So this will be an inversion. And if I insert in the fourth position, then 6 4, 6 2 will be an inversion. And if I insert in the fifth position, then 6 2 will be an inversion. If I insert in the last position, then there will be no inversions. But here we are only counting the inversions which have a 6 in the beginning. Okay, we are not counting the inversions which are already present here, and these will be counted by what is given here. Okay, so this is a combinatorial way to look at this recursion. I mean, you can solve this recursion. So if you solve the recursion, so there are many ways of solving this. So one way which is given in the book is by using induction, but another way could be also to use generating functions to solve this recursion. So I mean, the generating function approach is probably easier than the induction approach, but I'm not going to do that. So if you use whatever method you want, and if you solve this in recurrence, then finally we're going to get this answer. So in is equal to n factorial by 2 times n choose 2. So this is the answer that you are going to get. So this can also be explained combinatorially, and the way to do that is, so look at any random permutation on n letters. So let's call this permutation a1, a2 up to an. Okay, so this is a permutation on n letters. Now the reverse word. So okay, so some things I am using which are a combinatorial terminology, which should be understandable. So for example, letters are this a1, a2, an, etc. Words are combination of the letters. So this is a word a1, a2 up to an. This will be a word, and the reverse word will be an minus 1, and so on up to a1. Now both of these, this one and this one, both of these are permutations. So if this is sigma, then let's call this a sigma hat. Now any two pairs of numbers is inverted either in sigma or in sigma hat. Suppose I have a ij which is satisfying this condition. So I is less than j, but sigma I is greater than sigma j. If I have this condition in this permutation, then in the opposite permutation, this will be, so I is less than j, but sigma I will be less than sigma j in this case, because we're reversing the direction. And if there is a pair of numbers here where this inequality is satisfied, then in the other reverse permutation, the opposite inequality will be satisfied. So if you pick any two pairs of numbers, then either in this sigma or in this sigma hat, they will be inversions. Okay, so either they're an inversion in sigma or they're an inversion in sigma hat. So how can you pick pairs of numbers out of n letters? So the possibilities are n choose 2, and the total number of permutations, the total number of possible values of sigma is n factorial. So the total number of inversions will be exactly this. So sorry, not exactly this. We have to divide by 2 because this sigma and sigma hat, they will come in pairs. So the total number of permutations divided by these pairs of permutations. So this is another combinatorial way to arrive at the explicit formula for the number of inversions. But what is this? What does this have to do with all this Q series and Q analysis? This is because we can very naturally define the Q analog of n by using inversions. So what we do now is we introduce Q weights. Okay. So let's look at a simpler example. So let's fix n equal to 3, and we list all the permutations of S3. So we can have 1, 2, 3, 1, 3, 2, 2, 1, 3, then 2, 3, 1, 3, 1, 2, and 3, 2, 1. So these are all the 6 permutations of S3. I mean the elements in S3. So let's count the number. So this is our sigma. Let's make a table. This is our sigma, and we'll count the number of inversions of sigma. So here, nothing is an inversion because 1, 2, 1, 3, 2, 3, all of these pairs, not any of these pairs are an inversion. In this case, there exists one inversion, which is 3, 2. This pair is an inversion. So there is a one inversion. So in this case also, there is one inversion, which is 2, 1. Similarly, in this case, we have two inversions, 2, 1 and 3, 1. So two inversions. In this case, we have two inversions, 3, 1 and 3, 2. Again, 2. And in this case, all of the pairs are inversions. So 3, 2, 3, 1 and 2, 1, all of them are inversions. So we have 3 inversions. Now we are going to give Q weights, and the weight is Q raised to the power inversion of sigma. So Q raised to the power inversion of sigma. Then the weight here is Q to the power 0. The weight here is Q to the power 1, Q to the power 1, Q square, and Q3. Now let's calculate. So let us calculate what this is. Q raised to the power inversions of sigma in S3. Okay, for our case. So I'll have 1 plus 2 times Q1, which is just 2 times Q. Then I'll have 2 times Q square, and finally QQ. Now this is a nice polynomial, and we can factor this. So 1 plus Q is a factor. So if I take out 1 plus Q, then I'll be left with 1 plus Q plus Q square. Right? So this polynomial factors up nicely. So this is the weighted count of the inversions for S3. Now let's go back to the previous process that we highlighted about inserting a 4 in this case. Okay, so let's look at what happens if we insert a 4 in all of these permutations. So we can insert a 4 in all of these permutations, and we'll have some extra permutations as well where we need to calculate the number of inversions. So now let's see what happens if I insert a 4 in the first position. Okay, so I'm going to just do this, and then we'll see what happens to the Q weight. Okay, so if I insert a 4 here everywhere in the first position, then we'll add actually 3 more inversions to each of these. So because 4, 1, 4, 2, 4, 3, there will be 3 pairs which will be an inversion. So everywhere we are going to add 3 to the inversions. Okay, similarly here 4, 2, 4, 1, 4, 3, all of these will be inversions. So we are going to add a 3 to the number of inversions. And similarly, the weight will get increased by q raised to the power 3. So everywhere we are going to raise it by 3. Okay. Now, if I insert the 4 in the second position, then we are going to increase the number of inversions by 2. Because if the 4 would have been inserted here, then only 4 2 and 4 3 would be the new inversions that we have to count. So instead of a 3, we would have to increase the number of inversions by 2 and the weight by q squared. Similarly, if the 4 is inserted in the third position, then the number of inversions increases by 1 and the weight will increase by q. And if it is inserted in the fourth position, then there is no inversion which is coming up. So we don't need to add anything to the number of inversions, as well as we don't need to multiply anything to the weights. So if we do this process, then what we are going to get is actually so this polynomial will stay the same, and this will be repeated 4 times, right? So we will be repeating this polynomial 4 times. Okay. So from this discussion, from the above discussion, if we just do this, then this polynomial will remain the same. So we have 1 plus q times 1 plus q squared. Now, if I insert the 4 in the first position, then I am going to multiply each of these weights by q raised to the power 3. So I need a q raised to the power 3. If I insert it in the second position, I am going to multiply the weights by q squared. So I have a plus q squared. And then similarly, for the third position, I have a q1, and the fourth position, I have a q raised to the power 0. So if I just rearrange the term, then I get something like this: 1 plus q squared plus q3. Now I think you see where this is going. So there is a very general formula, and this is called Rodriguez formula or Rodriguez theorem. So let me just write down the theorem. So the theorem states that if instead of S3 and S4, you just take Sn, then the polynomial that we are going to get is this. So and so on up to 1 plus q squared up to q to the power n minus 1. So this is the inversion polynomial, if you would like to call it. Now these numbers, these polynomials, 1 plus q squared and 1 plus q squared plus q3 and so on, these polynomials are called the q analog of the numbers. Okay, so I'm going to define a q analog of n, and this q analog is just this. So if you make q go to 1, then we have that nq is just equal to n. Okay, so that is why this is called a q analog. So basically, this is just the weighted count of the number n, if you'd like. And similarly, we define n factorial q. Sorry, the factorial has to come outside. So similarly, we define nq factorial to be 1q, 2q, and so on up to nq. And this is exactly this polynomial, right? So whatever I have this here. So this is a very nice representation of the inversion polynomial. Now, how does one prove it? So again, there are many ways of proving this. And actually, we have already seen a proof, which is by induction. So I mean, sort of like a combinatorial induction. So we have shown that this is true for n equal to 3 and 4. It will be true for n equal to 1 and 2 as well. And then just assume that it is true for n equal to k, and just insert k plus 1 into all the permutations on n letter and on k letters then. And you are just going to multiply it by 1 plus q plus up to q to the power k. So that's a very nice short combinatorial proof of Rodriguez theorem. I mean, you can also prove it in other ways, but I think this should be okay. So from here, actually, if you put q, if you take the limit of q as it goes to 1, then you should get back the number of inversions. So if q is just 1, then this is just counting the number of inversions, right? So you should get back the number of inversions if you take q equal to 1 somehow. And one does get that. So let me just get it as a corollary. So I'm not going to prove it, but I'll just give you as a corollary. So let me also use some simpler notation. So for example, this n factorial q will be what I have been using for this notation. Okay, so I mean this will be simpler notation. So you can see that 0 factorial q is just 1. Then I mean there is another way also to look at this. So this is 1 plus q plus 1 plus q plus q square and so on up to 1 plus q to the power n minus 1. So if I multiply both sides by 1 minus q to the n here, then I can write it in a different way. So I take one factor from 1 minus q and then multiply it with 1 plus q, and I'm going to get so let's keep one factor, 1 minus q. Then the next one, if I multiply 1 minus q with 1 plus q, I'm going to get 1 minus q square. If I multiply 1 minus q with this particular quantity, 1 plus q square, I'm going to get 1 minus q cube, and so on until multiplying 1 minus q with this quantity, I'm going to get 1 minus q to the n. So divided by 1 minus q, 1 minus q, and so on. Okay. So this is another way of writing this n factorial q, and each of these numbers will be actually 1 factorial, sorry, 1q, 2q's, and so on up to nq. Okay, and this motivates us to further define the q Poghammer symbol. So the normal Poghammer symbol is defined in this way. So ak, this is called the Poghammer symbol or the rising factorial. So what you do is a times a plus 1 and so on up to a plus k minus 1. Similarly, there is a falling factorial, if you would. So anyway, so this q Poghammer symbol is similar to this definition. So we start with 1 minus q, and then the next product will be 1 minus q square. So we are going to increase the power here, okay, and so on up to, sorry, there has to be n here, up to 1 minus q n minus 1. So you can see the similarity here. So instead of just, this is a additive sort of analog for the multiplicative case here. So I had 1 minus q to the 0, 1 minus q, sorry, 1 minus q to the 1, 1 minus q to the 2, and so on up to 1 minus q to the n minus 1. Okay. So this is n. Sorry, I need this to n 1 minus q to the n so that it matches up with the, whatever is in above. So for any integer, I have this, and if n is equal to 0, then this is actually just 0. Okay, so this will be my definition. I can have a more general q analog of, sorry, I can have a more general q Poghammer symbol, and this will have two parameters now, not only q but also a. So let me also take the opportunity to define it. So there will be again two cases depending on whether n is equal to 0 or n is greater than 0. So I mean, we can also define it for negative n, so that we are going to do soon, but not right now. So for n equal to 0, this is just 0, and for n equal to so for n not equal to 0 but n a natural number, this is just 1 minus a, then 1 minus a q, and so on up to 1 minus a q to the power n minus 1. So for n, 0. And it's easy to see that if you put a q here instead of a, you get back the previous one. All right, so these are the notations that we are going to use. So let's look at this corollary of, I mean, I'm not going to prove it, but I'm going to give you the steps. So as a corollary of Rodriguez theorem, we want to see that the number of inversions is equal to this quantity. So there are three main steps to do. The first step is to just take the polynomial in Rodriguez theorem and take the log of this polynomial. So if you take the log of this polynomial, then using the Rodriguez theorem. So this polynomial was a product of different polynomials. If you take the log of product, it becomes a sum of logs. So this becomes a sum, k to 1 to n log 1 plus q up to q to the power k minus 1. Now we will so now if you differentiate with respect to q, you'll get some quantity. So this is step 1. So now step 2 would be to differentiate with respect to q, and then step 3 finally would be to set q equal to 1, and then you are going to get so then you are going to get something like this. So the sum of all the inversions sigma of Sn is equal to n factorial times this sum, so which is 1 plus 2 up to k minus 1 divided by k, and here k goes from 1 to n. So if you just use the formula here, you're going to get the result. Anyway, so these are the 3 steps to get the number of inversions as a corollary of Rodriguez theorem. But so far we have only defined the q analog of n and the q analog of a factorial, but in fact there is a q analog of the binomial theorem of the binomial coefficient as well. So that is what we are going to do now. Again, we are going to focus on inversions, but this time we are going to focus on a different type of inversions. So let's consider sequences of zeros and ones. So what are these? So we are going to consider sequences of k zeros and n minus k ones. Okay, so in total our sequence consists of n numbers. Out of them, k of them are zeros and the rest of the numbers are ones. Okay, so these are just binary sequences, but I mean in binary numbers you are not allowed to have a zero in the beginning, but in our sequences we allow the zero. So all of the terms in our sequence will be of length n. So for example, if n is equal to say 4 and k is equal to 2, then we'll have 8 possibilities, and these possibilities are, so I'll have 0 0 1 1, then I can have 0 1 0 1. So basically 2 ones and 2 zeros. Okay, so and then another one is 1 0 1 1. Sorry, not 8. We have 6 possibilities because 4 choose 2 is 6. So 0 0 1 1 0 1 0 1 0 1 1 0. Then let's start with 1 1 0. Sorry, 1 0 0 1, 1 0 1 0, and 1 1 0 0. So these are the different possibilities if we fix n equal to 4 and k equal to 2. Now we are going to define an inversion in these sequences. So we'll call a pair. Again, we are focusing on pairs of numbers. We'll call a pair an inversion when in that pair the 1 comes before a 0. Okay. So for example, here if you look at all the pairs 0 1 0 1 0 1 0 1 1 1, so here there is no pair where 1 comes before a 0. Okay, in the last pair there are 2 ones, so we don't have to bother about it. So the number of zeros, so let me just write. Okay, inversions are now pairs where 1 comes before a 0. So this is our sequence. This is the number of inversions, and again we'll have a q raised to the power inversion. So this is just 1. So here, if we look at all the pairs, so 0 1 0 0 0 1, there is 1 0 1 0 1 1 and 0 1. So in this particular pair 1 0, we have a 1 which is appearing before a 0. So the number of inversions is 1, and the q power is q. Again, similarly here, if we look, there are 2 now inversions. So this is 1 1 0, this pair will be an inversion, and 1 0, this pair will be an inversion. So the number of inversions is 2 and q square. And similarly, we do the same thing for here. So 1 0 1 0, again we have 2 pairs, so we'll have a q square. Again 1 0 1 0 and 1 0, so we have 3 now inversions here. And for this case, we'll have 4 inversions because 1 0 1 0 1 0 1 0. So there are 4 pairs. So q to the power 4. Now, What about this polynomial that we have got here? This is a more, this is a different polynomial than the previous polynomial. So I have 1 plus q plus 2q square plus q cube and plus q to the power 4. So if you look at the previous example, for length 4, the polynomial was much different and quite longer. So this was the polynomial for length 4. So you had these three products. This time the polynomial is a bit shorter. I mean, shorter in the sense that you still have the same powers, but the coefficients are different. Okay, so let's try to factor this polynomial now. Okay, so what I'm I mean, I'm going to just write it down and maybe so maybe it might be, so let's try to factor this. Okay, so I can have a 1 plus q as a factor, right? So if I have a 1 plus q as a factor, then I have a 1 here. No, I can't have directly, so I need to add and subtract something. So let me just write it down, the answer that we are supposed to get, and then I'll give you the factor. So I'm saying that this is equal to this quantity. Okay, so let's do it. 1 plus q, 1 plus q plus q square, 1 plus q plus q3. And then I have 1 plus q, 1 plus q. So yeah, so this 1 plus q and 1 plus q gets cancelled. Now if I do this, so 1 plus q times 1 plus q cube plus 1 plus q squared plus q to the power 5. So divided by 1 plus q, and I think I can so did I make a mistake somewhere? So 1 plus q, I'm going to multiply it by this whole quantity. Q square, I'm going to multiply it here. So I think there is a mistake that I made, because q5 should not appear. You see what mistake I made? Or maybe it's easier. Let's see. It's easier to use the other definition that we have. So let us use that definition. So the other definition was 1 minus q to the 4 divided by 1 minus q times 1 minus q by 1 minus q square times 1 minus q by 1 minus q square. Now this 1 minus q goes. I can cancel out a 1 minus q from here. This becomes a 1 plus q. I can cancel this out. This becomes a 2 and this becomes a plus. Did I make some mistake? It's not supposed to be this. Do you see the mistake or the factorization that I did? Let's go back. Let me check my notes if I made some mistake. Okay, so this is 0. That's right. Q square. Q square is fine. Q cube is fine. Q to the 4 is fine. Right. Okay. So these are, I have understood the mistake. So these were all the numbers that I'm taking, no? So these are the Q analog of the numbers, not the Q analog of the factorials. So which is the mistake that I have been making. Okay, sorry about this. So let's try to fix it. So this is still okay. So I'm going to get this. But this 4 factorial cube, it just means 4q, 3q, 2q, 1q, right? Divided by 2q, 1q, and 2q, 1q. So these 2's will go, these 1's will go, and this is just 1, so we don't need to care about that. So let's forget this. Now this is just equal to 4q times 3q divided by 2q, and this is now equal to 1 minus q to the power 4 divided by 1 minus q times 1 minus q cube divided by 1 minus q into 1 minus q divided by 1 minus q square. So this goes, and then now I have 1 plus q square. If I just divide this quantity and this quantity, and if I divide this quantity and this quantity, I'm just left with 1 plus q squared. And if I now expand this, then I have a 1 here. Then the power of q will be a 1. Sorry, the coefficient of q will be a 1. The coefficient of q square will be 2. So one's here and one's here. So this is 2. Coefficient of q cube will be 1. So q square times q. And the coefficient of q4 will be 1. So q square plus q square. So now this is okay. So we have seen that this polynomial is actually equal to this. And this should remind us of binomial coefficients, because 4 choose 2 is nothing but 4 factorial divided by 2 factorial times 2 factorial. So this actually, if you do one more step further, then you are going to get the q analog of the binomial coefficient, which is defined as follows. So n choose kq is now defined as n factorial q divided by k factorial q n minus k factorial q, when n k are integers and 0 is less than equal to k is less than equal to n, and this is 0 otherwise for all other values. Okay, so another way of writing this using the notation that we just introduced, this is qqn divided by qqk times qqn minus k, 0. So the range is same. All right. So now this is our definition for the q binomial coefficient. And from here we get a theorem. So I mean, not from here, but there is a theorem which says, so let S k n minus k be the set of all sequences defined above. So which was that these sequences are of length n with k zeros and n minus k ones. Then this quantity, so sum of all the sigmas in this set of sequences S k n minus k q raised to the power inversion of sigma, this is equal to n choose k q. So basically this is the q binomial coefficient. So there are two things that, I mean, there is one thing which in particular this should tell you is that it's quite remarkable that these q binomial coefficients are polynomials, because this side is a polynomial. So if this side equals this side, then this side has to be a polynomial. So it's like the binomial coefficient. So it's not, from the definition, it's not clear that the binomial coefficients are integers. One has to prove that these are integers. Similarly, from the definition of the q binomial coefficient, it's not clear that these q binomial coefficients are polynomials in q, but this theorem actually says that it's a polynomial in q. So how does one prove this? To prove that, one needs to use a famous recurrence, which is called Pascal's recurrence. So I mean, I'm sure you already know Pascal's recurrence for binomial coefficient. So there exists a similar recurrence for q binomial coefficient. Sorry, for this, yeah, so for q numbers, and this recurrence is nq is equal to kq plus q to the power k n minus kq. So this is very easy to actually prove this. So this is how do I say this? The recurrence for the q analog of numbers, and there is a recurrence for the q analog of binomial coefficient, which is the following. So n plus 1 k choose k q is equal to n choose k q plus q raised to the power n minus k plus 1 choose n, sorry, times n choose k minus 1 q. So this is called Pascal's recurrence. Again, it is easy to prove. One just needs to equate both the two sides, and they will come out to be equal. So while doing that, maybe you might have to use the first line. So the proof of this, it's a computational exercise. So one just has to show that. So this side obviously satisfies the Pascal's recurrence because we have defined, I mean, not defined, but this recurrence is in terms of the Q binomial coefficient. So this binomial coefficient will satisfy the recurrence here anyway. So one needs to then show that this side satisfies this recurrence, and for that we need to use combinatorial techniques. So this is how the proof goes. I mean, the next step of doing this whole generalization of Q analogs would be the Q multinomial coefficient. So in general, so I mean, the multinomial coefficient is defined as so n, say a1, a2 up to ak. This multinomial coefficient is just n factorial divided by a1 factorial, a2 factorial, and so on up to ak factorial. Okay, so I mean, so the natural way would be to just add a q here. Everywhere if you put a q, then this would be the Q analog of the multinomial coefficient. But the thing is that this actually counts something. So like the multinomial coefficient, it counts something. So the Q analog of the multinomial coefficient also counts something, and that something is again number of inversions for a more general sequence. So in the previous sequence, we had only two letters, 0 and 1. But if we don't restrict ourselves to two letters, if we allow say many letters, so let's define a sequence. So Sn k1 up to km. So this is the set of all sequences such that of length n. So of length n, this is important, with ki occurrences of I. Okay. So in the last case, we had this just m was 2, then we had k1 ones and k2 twos. So this one, I mean, it does not matter if you use 0, 1 or 1, 0, 1, 2. So these were the so this was the analog of the sorry, this was the special case of the last example that we looked at. And in this setting, the number of inversions would be the number of pairs where 2 appears before a 1. But here we can use the normal definition of the inversion that we are familiar with in terms of the permutations. Okay, the only difference with the permutation is that from here actually we can get Rodriguez formula, because in permutations all of these ki's will be equal to 1. So each number I occurs exactly once in a permutation, but here there is no restriction on the number. So if we restrict this ki to be equal to 1, then we'll get Rodriguez formula. So this is actually equal to something like this. So sigma belongs to S k1 Sn k1 up to km q raised to the power the number of inversions of sigma. And as a corollary of this, if ki is equal to 1, then we get this. So Sn q raised to the power inversions of Sn is equal to now so sorry. So this was the result of Rodriguez. It's also easy to see, because if everything is 1 here, so 1 factorial times 1 factorial and so on up to 1 factorial, then, oh sorry, I mean this should be a k, okay, if I'm using a k here. So this should be a k. Anyway, so if you put all the k's equal to 1, then everything here disappears. So you are just left with n factorial q, which is what Rodriguez formula is. So anyway, I understand that this might be a bit fast, but this is just like to give an idea that there is a natural way to go to Q analogs of binomial coefficient as well as multinomial coefficients and so on. But let's also look at another direction, which is the Q binomial theorem. So I mean, after we look at binomial coefficients, the next general thing to look at would be the Q binomial, the binomial theorem. And there exist many analogs of the binomial theorem now. So that's one issue with the Q world, because okay, it's not the only example. So for example, One can also define Q analogs of Catalan numbers. So these are like combinatorial objects. So Catalan numbers Cn is just these numbers, okay? And these numbers, they count many things, and one of them is like dig paths of length 2n. So what are these dig paths? So you have this you have the x-axis and the y-axis, and these dig paths of length 2n are lattice paths now, where there are only two possible steps. So either you go up or you come down, okay? So you can keep on going up and then you come down. So so dig paths, they have this criteria that the number of up steps is equal to the number of down steps, and you don't cross the x-axis. So that means you cannot, like, this path is not allowed, okay? So you can just touch the x-axis and then you have to again go up and down until you reach this position, which is 2n, 0. So these are dig paths, and the number of dig paths of length 2n is counted by this Catalan number. Now, if you do the naive Q analog of Catalan number, let's call it like C and Q, then we would think that the Q analog would be this, right? N plus 1 Q, and then 2n choose n Q. But I mean, this is one possibility of the Catalan, of the Q analog of the Catalan number. So this has to count something for it to be a true Q analog, and this has to count something which is related to dig path, so that it gives you some sort of like similar relation between the both numbers. So for dig paths, there are many natural ways of giving the weight. So one way would be to count the area under the path. This would give you a nice Q weight, okay? And there are other possibilities of also doing that. So one way would be to count this area under the path, okay? So Q raised to the power the area for a dig path. And if you do that, this is not actually what comes out. So this quantity is not equal to that Q analog. So there is a different Q analog for that. So I mean, the point is that there might exist more than one Q analog for a particular combinatorial quantity, and the same thing happens for the Q binomial theorem. So there exists more than one Q analog of the binomial theorem, and I'm going to just state maybe we can do it later on. So for example, I think there are 3 or 4 Q analogs of the binomial theorem given in the book, and the one that we are going to use repeatedly is called Rothe's Q binomial theorem, which is, I think, the most natural way that I would think of, because it also gives a combinatorial interpretation in a very nice way. Anyway, so we are going to do that next time. The objective of this time was just to introduce the Q analogs of different things. I mean, so these Q numbers, they come quite naturally in partitions, as you all know. So I mean, so I'm not going to define partitions, but we have this generating function for partition Pn Qn is just 1 over QQ infinity, and this symbol QQ infinity is just limit n goes to infinity of QQn. This is one way. I mean, okay. Anyway. So this is the generating function for partitions. The generating function for distinct partition, so PDN will be distinct parts partition, is equal to this 1 plus Q to the I, and I greater than equal to 1, which is equal to minus Q infinity. So again, if we just restrict the partition to odd parts, let's call it PO of n, then the generating function is 1 over Q squared Q infinity. So you are just taking the odd parts in this case, okay? So, and there is a very famous theorem of Euler which says that this quantity is equal to this quantity. Anyway, so let's try to prove one result using Q. So not one, actually 2 results. So the first result on partitions that we are going to prove is the following. So let T1n is equal to the number of partitions of n where odd parts may be repeated. So the number of partitions of n where odd parts may be repeated. But even parts are distinct, okay? So, but even parts are distinct. And T2n is now the number of partitions where no part can be used more than 3 times. So the number of partitions of n such that no part appears more than 3 times. So I mean, so you understand what this means. So we are going to give a Q series proof of this result. So what is this T1n, the generating function for T1n? So this consists of two pairs of two partitions. One partition is just where even parts are distinct, and the other type of partition is just where you have only odd parts and these parts may be repeated. So for the odd part, partitions with odd, sorry, I think this is Q square here, not here. Otherwise, this is just, anyway. So for the odd parts, this is just 1 over Q square infinity. And then for now, the even parts distinct, I replace the Q by Q square. So this is the generating function for T1n. We are now going to simplify this generating function a bit. So let me just write it. So anyway, so I mean, if I use the Euler's odd distinct thing in this particular case, then this minus Q square infinity just becomes Q square Q4 infinity. Okay. So in the place of Q, I want to replace this by Q square. So this remains the same. By using Euler's result, this becomes Q square Q4 infinity. Now we are almost done. So what this gives us is, so 1 plus Q square up to Q cube, right? So I mean the first, okay, for this I need to use this. So I'm sure you already know. But since we are in the formal world, all of these are polynomials for us, so we don't really care about convergence or divergence. So for us, this is always true, okay? At least, I mean, for whatever I'm going to say, this is always true. So if I use this, then I'm going to get, the first thing I'm going to get is 1 plus Q square up to Q cube. Then the next thing I'm going to get is 1 plus Q square plus Q4 plus Q6, and then so on, okay? And what is this? This is just the generating function for T2 of n. Because here, each part can appear at most 3 times. So the part 1 appears at most 3 times, the part equal to 2 appears at most 3 times, and so on. So this is a nice generating function proof, actually. So, but from here to here, there are many steps actually. So at least there are, I think, 1, 2, 3, 3 steps will be there. So how one gets this would be an exercise. Okay, so from here, how to come to this particular case would be an exercise. Anyway, so I'm going a bit fast because there are 2 more results that I want to show. And this is a result by Kelly, which is an important result. It says the following: the generating function for partitions into at most I parts such that each part is at most j is this quantity I plus j, choose j q. So how does this partition look like? If you make the Ferrer's diagram, these partitions will be, the shape will be something like this, where this is less than equal to I, and this is less than equal to j. Okay, and the very nice result of Kelly is that these numbers are given by The generating function for these partitions is a very nice Q binomial coefficient. And the proof is very combinatorial. One can do the following. So if you look at a rectangle of size, say I plus j and I, this is a rectangle. And then I want to make lattice paths starting from this point. Let's call this point 0, 0 to this point, which is the point ij. Is it I? Sorry. What I'm doing? This is just j. Okay. This length is j. So this is ji. Maybe I'll make it j and make it I. So this is ij. Okay. So I want lattice paths from the point 0, 0 to ij. And the path can have only two particular steps. One is a east step and the other one is a north step. So basically paths of this type. Okay. 1, 1. So of this type will be something like this. So these paths are allowed. Now, if you look at these paths are actually partitions of exactly this type. So if you just divide this into boxes, then you can see a nice partition appearing. Okay. So what is this partition? You can take either. So there are actually pairs of partition, but for me, I'll just consider this because this is the j that I fixed in the top. So if you just take the dots here, this is a partition which is appearing of exactly the type that we have, right? So this partition, the dots, the partition that is represented by the dots have two criteria. So one criteria is that the largest part is at most j. So this condition is satisfied. And the number of parts is at most I. So this condition is also satisfied. So these lattice paths are actually in one-to-one correspondence with partitions of the type that we want. And now this problem of finding the generating function for these partitions is actually equivalent to finding the generating function for the lattice paths, where the weight of a lattice path is now the number of dots which are below the path. So basically this would be the weight. So q raised to the power the number of dots which are below the lattice path. So what this result is saying is that I mean, I can actually give you a proof because the proof is not difficult for this. So if you remember, if you go back, we discussed this nice recursion of Pascal, and we can see this recursion actually come out of this picture. So how can we see this? You see, there will be two different types of two different things that can happen. So one of them is actually happening here. So the thing that can happen is that the first step can be a E step. And if the first step is a E step, then this whole strip is actually gone. We don't need to count this strip at all. So if the first step is an E step, then the picture, it decreases actually. So the number of, so the rectangular shape would now be of size I minus 1 j. And it might also happen that the first step is a north step. So if the first step is a north step, then this strip is always included. So that means a power of q to the power I will be always included in the area of the path. So we can exclude this and then just think of the lattice path in the smaller rectangle, j minus 1 to I. So this will actually give two cases, and we can break the generating function into two parts. And each of these part, if we just combine them together using Pascal's recurrence, we are going to get this particular result. So, I mean, the point was that combinatorial thinking, it can give nice Q series results. Another example is a famous result of Jacobi. And Jacobi's result is the following. So 1 over QQ infinity is equal to, so this is an infinite product, and now we are going to write a sum expression for this infinite product. Q raised to the power n square divided by QQ n square. So this is the generating function for partitions. This side should also be the generating function for partitions. And how we are going to find this generating function, how we are going to find this quantity as a generating function. So for any partition that we have, we can make the largest square, which is called the Durfee square. Okay, so I mean, this will be the Durfee square. So if there is a j boxes, if the size is j and j here, then the number of squares is j square, and whatever is below this Durfee square will be a partition, and whatever is to the left, whatever is to the right of this Durfee square will be another partition. But the condition is now that the largest part of this partition, which is below, will be of size j, and the partition which is to the right will have at most j parts. So this whole one partition we have broken up into 3 different parts. So this q raised to the power n square comes from this square, and this qqn, one qqn comes from the partition below, and one qqn comes from the partition to the right. So this is a very nice and easy combinatorial proof of Jacobi's result. We can also, maybe as an exercise, we can also have this nice result, which is that the number of self-conjugate partitions of n is equal to the number of odd distinct partitions. So that means odd parts are distinct partitions of n. Yeah, I mean, so I just wanted to mention until this point, but this does not really correspond to chapter 1, because I think some of these things also appear in chapter 2. But the main idea was that we wanted to focus on Q&A logs of different quantities, Q&A log of a number, Q&A log of a factorial, Q&A log of a binomial coefficient, and Q&A log of a multinomial coefficient. So yeah, I mean, that's it. So I mean, next time maybe we are going to do the Q binomial theorems.